Hello subscribers and viewers of this channel. In this video I will explain one very important test for determining the stability of dynamical systems. I will explain the Routh-Hurwitz stability criterion, and I will explain how this important test can be used to investigate the stability of dynamical systems. In order to make your life easier and in order for you to better learn this important topic, I created a post that nicely summarizes everything that I will explain in this video. As you can see, this post contains equations, examples, and old explanations. A link to this post is given in the description below. Please don't forget to press like and subscribe buttons. Thank you very much. Okay, so let's start. The main idea of the Routh-Hurwitz stability test is to determine if a system is asymptotically stable without explicitly finding the roots of the characteristic polynomial. This criterion was established well before digital computers were invented, and naturally some of you might ask me the following question. Well, if that's the case, why do we need this criterion? Is this criterion still useful? The answer is yes, we still need this criterion since it can give us a range of control parameters that will guarantee system stability. For example, when you want to tune a PID controller, this criterion can give you a bounds on proportional, derivative, and integral parameters or gains that will guarantee the system stability. Let the characteristic polynomial of the system whose stability we want to investigate be given by this equation over here. A1, A2, A3, A4, A5, and A6 are coefficients, and S is a complex variable. Here, for presentation clarity, we assume the system whose model order is equal to n is equal to 6. However, everything explained in this video and in this post can be generalized to system with arbitrary state orders. Now, let us briefly recall the necessary conditions for the stability of this system. The first necessary condition is that all the coefficients of the characteristic polynomials have the same sign, and the second condition is that none of the coefficients actually vanishes. Here, we need to stop for a second and mention one very important fact. Namely, these are not sufficient conditions. The Routh-Hurwitz stability criterion will actually give us the necessary and sufficient conditions. And to apply the Routh-Hurwitz stability criterion, we need to construct the Routh-Hurwitz table. This table is given over here, and in the sequel, I will explain you how to construct this table step by step. The first row of the table is populated as follows. First, we identify the coefficient multiplying s to the power 6. This coefficient is actually the coefficient a0, and it's equal to 1. We take this coefficient and we place it over here. So this is our a0 and it's equal to 1. Now we take a2 and we place a2 over here. We take a4 and place a4 over here. And finally we take a6 and we place a6 over here. Now, what's the principle for populating the first row? Well, the idea is to take the coefficients with an even subscript or with an even index and to populate the first row of this table with these coefficients. Here is a0, here is a2, a4, and a6, and all these indices are even, or better to say, all the subscripts are even. Now, that's our first row. How about the second row? For the second row, we take coefficients with the odd index or with the odd subscript. So these coefficients are a1, we take a1, we place a1 over here, we take a3 and we place a3 over here. Here's a5, it goes here, and since here we have 0 multiplying s to the minus 1. Here is our 0. Okay, to repeat everything from the beginning, first row are basically coefficients with an even index or with an even subscript. And the second row are coefficients with an odd subscript or with an odd index. Once we populated the first two rows by using the coefficients of the characteristic polynomial, we can also populate all other rows by using a simple recursive principle that I will explain in the sequel. First, we explain how to compute the coefficient A31. Here the subscript or index 31 means that this entry belongs to the third row and the first column. So here is the graphical explanation of the idea for the computation of this coefficient. We take A1, we multiply A1 by A2, then we place a minus sign, then what do? We take A3 and we multiply A3 by A1 and divide the result by A1. We apply the same idea in order to compute the coefficient A32. Again, we take A1, we multiply A1 by A4, then we place a minus sign, and we take A5 and multiply A5 by 1, and we divide the result by A1. Similarly, we compute the coefficient A33. Again, we take A1, we multiply A1 by A6, we place a minus sign that you cannot see over here because I have a 0 over here that multiplies 1 and that gives you 0, and we divide the result by A1. Coefficients belonging to other rows are computed in the same manner. So let us explain how to compute A41. Now, instead of taking A1 as the first entry, we will take A31 since we went one row below the second row, or actually one row below the third row. So what's the idea? Now we take A31, we multiply A31 by A3, we place a minus sign, then we take A32, we multiply A32 by A1 and divide the result by A31. Okay, that's easy. But how about this coefficient, A42? Again, the principle is the same. We take A31, we multiply A31 by A5, then we place a minus sign and take A33 and multiply A33 by A1 and divide the result by A31. And you can see it over here. So A42 is A31 multiplying A5 minus A33 multiplying A1 divided by A31. So how about the entry over here? Well, the entry over here is equal to 0, and you can verify this by yourself. Now, how about the coefficient over here? Let us apply the formula. Let us apply the same recursive principle. So, what do? Since we went one row below, we will take A41, we will multiply A41 by A32, then we place a minus sign, then we take A42 and we multiply A42 by A31 and divide the result by A41. Similarly, this coefficient over here, A52, is computed as follows. Again, we take A41 and we multiply this coefficient by A33. We place a minus sign that you cannot see over here because over here I have 0 that multiplies A31 and that's 0, and we divide the result by A41. Besides this approach, there is another approach for computing these coefficients, and the results will be the same. That is, both approaches should give you the same coefficients. Now, let us explain this approach. This approach relies on determinants and on matrices. Now, in order to compute A31, we will basically need to construct this matrix over here, and we will need to compute the determinant of this matrix that you can see over here. Once we compute the determinant, we simply divide the result by A1 and place the minus sign, and the result will be the identical result to the result that we obtained by using the first approach. Okay, so let us now compute the second coefficient in the third row, or actually the coefficient 3, 2, by using this approach. Again, we construct the matrix by taking these two terms and these two terms, and here's the matrix. Then we compute the determinant of this matrix and divide the result by A1 and place the minus sign, and again we obtain the identical A32. Similarly, to compute A33, we construct another matrix by taking these two terms and these two terms, or these two coefficients. We form a matrix that you can see over here, compute the determinant, divide the result by A1, and again we obtain the identical result. Other rows are computed in a similar manner, that is by taking the determinant of appropriate matrices. Just as an illustration, for example, to compute this term over here, we will basically take this matrix, compute its determinant, divide the result by basically A31 and place a minus sign, and to compute this term over here, we will basically take these two coefficients and these two coefficients, form a matrix, compute a determinant, place a minus sign, and divide the result by A31. Now we are ready to formally state the Routh-Hurwitz stability test. This test investigates the stability of a dynamical system by inspecting the sign of the entries of the first column of the table. And we can formally define this test or state it as follows. The roots of the characteristic polynomial are all in the left half of the S-plane if all the entries of the first column of the Routh-Hurwitz table have the same sign. Moreover, the number of sign changes of the entries of the first column is equal to the number of poles or roots of the characteristic polynomial that are in the right half of the S-plane. Okay, so let's go back to our table. First, we identify the entries belonging to the first column. Here are the entries. The Routh-Hurwitz stability criterion states that this system is stable if all entries have the same sign. Also, the Routh-Hurwitz stability test can tell us how many poles are in the right half of the complex plane by inspecting the sign changes of the entries belonging to the first column. For example, let us assume that the entries have the following sign: plus, 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 minus, plus, plus, plus. Now, the Routh-Hurwitz stability test tells us that here we have two poles in the right half of the complex plane. How did we determine that? Well, we see over here that we have a plus sign, plus sign, plus sign, and here we have a sign change. So this is the first sign change. So this gives us one pole in the right half of the complex plane. And immediately after a minus sign, we have a plus sign over here. So that's another sign change, and that's another pole in the complex plane. And if we go further, we see that the sign of the entries is positive, and we don't have an additional pole in the right half of the complex plane. So 1 plus 1 gives 2. So in total, in this particular case, we have 2 poles in the right half of the complex plane. For brevity and clarity of this video lecture, we don't cover special cases of the Routh-Hurwitz test. Special cases occur when the first entry in any of the rows is 0 or when all entries in a row are 0. And in order to illustrate you this situation that can sometimes actually happen, let us imagine that this coefficient over here is 0. That is that A31 is 0. Now, we can immediately see that in order to compute A41, we will have certain problems. This is because we divide this determinant by A31. And if A31 is 0, then we have a big issue over here. So A41 is not defined then. I will explain these special cases in my future videos and tutorials. Now, in the sequel, I will present two examples that illustrate the applicability of the Routh-Hurwitz stability test. Okay, so here's our first example. We want to investigate the stability of a system whose characteristic polynomial is given by the equation number 4. Here the coefficients are 1, -4, 1, and 6. And by inspecting the sign of these coefficients, we can immediately see that the coefficients of this polynomial do not have the same sign. Consequently, this system is not stable. This is because of the necessary conditions for the stability that are stated over here. Namely, the necessary conditions for stability are that all coefficients of the characteristic polynomial have the same sign and that none of the coefficients vanishes. In our case, obviously that's not the case, since we basically have sign changes over here. We have 1, -4, 1, and 6, and obviously here we have a negative coefficient and all other coefficients are positive, and consequently our system is not stable. In this case, the Routh-Hurwitz test can reveal how many roots of the characteristic polynomial are in the right half of the S-plane. So let us construct the test table. So here's our test table. Here's the first coefficient 1. Then we have the coefficient 1 over here. We have -4 over here. And we have 6 over here. And the rest of the table is constructed by using the recursive formula that I explained at the beginning of this video. Now, by inspecting the first column, we can observe two sign changes, from 1 to -4 and from -4 to 5 over 2. Consequently, the characteristic polynomial has two roots in the right half of the complex plane. And in fact, we can factorize the characteristic polynomial as follows. Basically, we can factor the roots or the poles, and we can see that the roots are s is equal to 2 and s is equal to 3. Consequently, this confirms the findings of the root stability criterion. Okay, so here's our example 2. This example is a little bit more complex since the construction process of the Routh-Hurwitz table is more tedious. So we are looking into the stability of a system whose characteristic polynomial is given by this equation over here. Here the coefficients are obviously 1, 4, 3, 2, 1, 4, and 4. Here is our test table. Here I will not explain how to construct this table in order to make this video as short and concise as possible. I explained the construction process in other parts of this video. Now, let us inspect the sign of coefficients belonging to the first column. Positive, 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 positive. Here we have a negative and positive. Now, we conclude that we have 1, 2, 3, 4, 5, 6 coefficients with a positive sign, and we have one coefficient with a negative sign. Consequently, since not all coefficients have the same sign, we conclude that the system is not stable. Again, since we have 6 coefficients with a positive sign and one coefficient with a negative sign, the system is not stable. Next, let us inspect how many poles of the system or the roots of the characteristic polynomials exist in the right half of the complex plane. Again, let us look at the sign: positive, 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 negative, and positive. So how many sign changes we have? Here we have one sign change, and here we have another sign change. So we are having two roots of the characteristic polynomial in the right half of the complex plane. Okay, that would be all for today. I hope that you like this video. If you like the videos I create, please press the like and subscribe buttons. Thank you very much and have a nice day.